Hi guys, this what you see is an old vacuum cleaner motor. Now if you look closely you will find the commutator, brushes and one of the field windings which indicates a universal motor. Now let's focus on the label. As you can see it's showing 50 to 60 Hz at 1000 watts. So guys, now it's time to open up the impeller casing of my universal motor. The impeller looks very nice, although I highly doubted that it is going to survive the water pressure if in the future I plan on using it as a water pump. So let's give it a spin before taking it out completely. Oh. So guys, before we start with the testing part of using a vacuum cleaner motor as an electric generator, let's take a look at these universal motor powered machines. So I'm going to choose an angle grinder to demonstrate that universal motors can produce large amount of electricity. Let's start with the connections. This what you see is the thread, the angle grinder, the wires and finally connecting to this bulb, 12 volts. Let's turn on the switch. So let's wound the thread and see if it glows. As you saw that I did not connect any external power source or battery for the field excitation of this angle grinder and still it produced electricity upon shaft rotation. Why is that? That is because of the self excitation and it happens only with few universal motor operated machines, not every universal motor. Now this one that you see is a very old type of universal motor and it is from a blender. Here as you can see is the commutator and the brushes. Now for close-up and inside view of the motor, you can see the armature and the field winding, not the magnets, but the field winding from where the wire is coming and joining the brush slot. Now let's connect a 60 volts DC e-bike charger to this motor and see how it performs. So guys, now that you have seen it in the motoring mode, let's test it as a generator, see if it can generate electricity or not. So guys, here as you can see that I gave it a spin, but it is not generating electricity. Now let's run it in the reverse direction. Okay, here is the knob in the drill for reverse operation. Now let's try it again. And now it is working as a generator. Okay. Oh. Whoa. So bright. So guys, the mixer and blender motor is also acting as a self-excited generator, but only in one direction. Here as you can see that I've already connected the drill machine to the vacuum cleaner motor, and to the output wires of the motor I've connected this bulb once again. Okay. Now let's reverse the direction of rotation. Reversed. Okay. For either case, it is not generating electricity. So to convert it into a generator, the first step is to disconnect the field pole windings from the brush slots. After that, take another wire and connect it to one of the disconnected wires of the field winding, like this. After that, calculate the length of the additional wire needed to connect it to the other left out wire from the disconnected winding. Now connect it to the left out wire. Now in total there are 4 connections left, 2 these blue wires and 2 these brush slots. Make sure that this additional wire is not touching any metal piece. Now take 2 jumper cables and connect it to the brush slots. So guys, here I'm going to use a fully charged 3.8 volts lithium ion battery, and as you can see that the bulb is glowing very dim. So guys, here I've connected a multimeter to measure the voltage because the bulb is not glowing, so I have to make sure what the problem is. Let's check the generated voltage. So as you saw that even after adding a 3.8 volts battery, the generated voltage is only a little bit higher than that, and since the bulb is not glowing, which means that the current is even lower. So it is a disaster generator. Let's increase the field input voltage by connecting a 12 volts UPS battery. Obviously this time the generated voltage should be higher, but let's see by how much. So the voltage increased from 5 volts to 10 volts almost, but it was not enough. Let's connect a bulb. So guys, the bulb did glow, and although it acted as a generator, but the power consumed by the field winding was much higher, and for that the bulb is going to glow much brighter directly. You see, it is much brighter this way. So I would say that this is the worst generator ever for vacuum cleaner motor, unless you decide to modify the armature winding. Starting with the components needed for the project, first one is the breadboard, second a ferrite core for making of the inductor, some copper coil like 20 gauge is what I'm using here, two 13009 power transistors and one universal board. Also you will need a 6 amperes diode. Take the core, place the wire through it, then bend it and go clockwise until it is completely full. Make sure that you do not overlap the wires. So after completing the winding of coils on the ferrite core, your inductor is going to look somewhat like this. You can see there is no overlapping and the winding is pretty good. And I have used 2 wires together as one so that I can increase the current flow through the inductor, which in turn increase the current flow throughout the circuit and more charging to the inductor. Now we can cut off this wire. After that comes the part of removing insulation. So guys, starting with the construction, these are 13009 power transistor and this one is the heatsink and this is heatsink compound. Let's place it. Now that the two transistors have been mounted on a single heatsink, I'm going to tell you its use later on. Let's move on to the testing part of this circuit on this breadboard. Starting with the connection part. Safety first. Okay, so guys, it's time to connect the power supply. Okay, so inductor is here. One terminal of the switch is done in the power source. Did you see some voltage increase? Yeah. Of course, it was not going to work with a simple switch as this one. Boost converter circuits are much more than a simple circuit. This switch SW1 is not any simple switch like this, but a high-speed switching circuit, and that speed goes to even more than 100 kilohertz, 100,000 hertz. That is the frequency or even more which is going to be applied at this point. Yeah, and this time here, as you can see that I've placed this red switch, and this is the push type switch and not the continuous on switch. The meter is showing 11.64 volts, which is almost 12 volts that we are getting from the power supply. Now because I'm going to use my hand frequency, the growth is going to be slow since I'm doing it manually, but you can see that the voltage has increased from 11 point something volts to 13.87 easily. You see, 14.56, and when we do it slowly, then it is not increasing. You see, that is why high frequency is needed. Higher the frequency, greater is the increased voltage, increased speed. You see, now I've stopped and it is 16.56. I'm feeding in 12.5 volts, sorry, 11.5 volts, and here I have reached 16.5. Let's go more. Let's see how much I can do. Yeah, we have reached 19 volts. 20 more. 21. 22. No. Move to 22. Fool. 22. Oh, come on, my connections. Yeah, we can do it. Yeah. So guys, as you saw that I achieved 22 volts from 11.5 volts, which was pretty good with simple manual switching. Imagine what will happen if I connect an actual switching circuit in place of this push switch, and that switch keeps on operating at a frequency which is more than 100 kilohertz. It is going to be awesome. So with that being said, let's put all this circuit on my universal PCB boards, link for which will be provided in the description. Don't forget to check it out, please. It is really high quality. So guys, these transistors mounted on the heatsink that you see are going to be the switch for the circuit that I showed you for the boost converter. After connecting your inductor comes your high current 6 amperes diode. So the diode has also been connected, as you can see, pretty good. Now comes the capacitor that I just used, 50 volts, 470 microfarad. So guys, as you can see that I have completed the main primary circuit for the boost converter. Now comes the part for making the driver circuit for this very switch, the transistor switch. This heatsink, two transistors are mounted on it, and this transistor switching set is going to be operated by the components here in this box. Starting with the circuit, the driver circuit. You see this one, the circle is one transistor, this is the second one, and this one are simply two resistors. Now I still have to decide the resistance value according to the current and voltage level of the IR emitter, which is going to send light signals to the receiver here. So guys, now comes one of the most important parts. This one, as I told you, is IR receiver, and this one is emitter, little bluish, this one is dark. So I will have to place them in this tube like thing. So this one is going to emit light and this one is going to receive light. And there's little gap, the lesser the better photons from this one to this one. And this is done because we don't want like external lighting from our rooms or sunlight to get in contact with the circuit. It's my design. I'm not sure if others also do that, but it works pretty good for me. And I will also have to use black tape because it is still not complete. Black tape is must. Now that is one part, the other one is still left out, the other end. I think now there should be no chance of escaping of light or external light coming in. Even if so, there is no worry. I'm still going to place this heat shrink tube. Now it is completely sealed. I don't think light can enter inside it. So guys, I have also completed the driver set, okay, and this is the IR emitter and receiver pack, and this is the 1:1 inductor, and that's the primary circuit that I completed before. Now this driver circuit will give switching signals on off to the inductor of the primary circuit. With the help of those signals, this inductor is going to turn on and off, and hence it's going to perform as expected. If you look at the circuit here, I have done certain changes, and I have also like improved the circuit design. Now as I showed you that this is the driver circuit and this is the final output transistor. It has obviously three terminals: base, collector and emitter. So here the collector and emitter terminals will be finally taken out from the driver circuit and fed to the base and collector terminal of this transistor on the primary circuit. And here you see two more terminals for the driver circuit. These two are for powering up the driver circuit. This black tape that you see, that indicates negative wire, and this one is positive. So either you can connect it in parallel to the black and red of the primary circuit, or you can connect an external power supply to the driver circuit. The input voltage for the driver circuit ranges from 0 to 20 volts. So guys, I've mounted both the circuits on this wooden board. Also the supply for the driver circuit, I've connected it in parallel to the primary circuit. Now all I have to do is connect positive on this terminal positive on this terminal and negative on the black one, and then output is going to appear on the positive and negative. Let's test it. So guys, for the testing part, here as you can see that I am using 12 volts 5 amperes DC supply from a laptop charger. So first I'm going to measure the output terminals from the power supply. This one, that's the power supply. So guys, as you can see that the meter is pointing 0 volts. Let's connect the power supply terminals to it. And now it is showing 12.06 volts. So it's a 12 volts DC supply from the charger. Now from the 12 volts laptop charger power input, I am powering up this circuit, and you should see the display voltage. Keep watching the display screen of the multimeter. You see, instantly the capacitor charged at more than 40 volts. It's displaying 39 volts right now. Once again, so 43 volts is the max I'm getting from 12 volts input. So guys, now it's time to test it on motors. This is a 24 volts DC motor. Okay, so let's power this one up. You see it's running. Oh, it is working so nice, guys. You hear the sound of its operation once again. Oh. You see, I'm trying to stop it, but still the output is pretty good. Although the motor is small, so obviously the power of the motor itself is not very high. Actually, the transistor pack on the primary circuit is quite hot. So guys, I forgot to tell you one thing, that the transistors have negative temperature coefficient, because of which the heating multiplies if they are connected in parallel. So my advice to you is use separate heat sinks and mount the transistors on them instead of using one single heat sink, as I did foolishly because I forgot about the negative temperature coefficient part. Use separate heat sinks and then it is going to work very nice. And also I forgot one more thing. I showed you the operation of this motor with the boost converter, but I did not show you its operation without the boost converter, so that you can compare the two, with and without part. So now without the boost converter and directly from the power supply, that's the max speed. You see it is stopping slowly, so easily. You see. The voltage is not enough. That's it. And the best part of this boost converter is that there is not a single IC that has been used for the making of this circuit. No IC has been used. It's all on transistors. So once again, I think you can compare the two. There is literally no comparison. The speed is very high for this. I'm really satisfied with the circuit. Let's move on to a bigger motor instead of this one. So guys, I found another motor, a little bigger one. It's from a reverse osmosis water pump. Again, 24 volts. So let's connect this one. Yeah, first from the 12 volts power supply directly. After that, I'm going to do the connection to the boost converter. You see, it's running so slowly. I'm feeding it with 12 volts right now directly from the power supply without the boost converter. Okay, keep watching the motor, guys. Speed has increased 3 times. This time it is running really fast. Now guys, I'm going to try and run this 360 watts e-bike motor. It is 36 volts and 15 amperes. Sorry, it's not 360. It is 36 volts, 15 amperes. So power is 36 multiplied by 15 amps. It is quite heavy. Let's run this one first without the boost converter. Comparison is must. Let's remove it, and yeah, that's it. Although the torque is pretty good because the motor is like really big with a big armature and coils. I cannot stop it. It's really slow. That's the point. Now here we are limited to the current from the power supply, which is only 5 amperes. At present it is a 15 amperes motor, but running at only 5 amps because it is running under no load. It's not fully loaded. So obviously it is not going to draw 15 amps. That's just common sense, right? Okay, now comes the part of running it at full power with the boost converter. Okay. Okay. Wow. You see, it is running so fast. And the torque is also very good considering the power supply that I'm feeding, although the transistors are going to heat a lot because the motor is very big here. Wow, 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 5 times wow. Wow, it is so cool, guys. I'm loving this circuit so much. Let's increase the load further by yeah, I have another 500 watts. Most of you must be familiar with this motor. It is available in the market, 24 volts, and the current rating is 26.7 amperes. It's very heavy. Now I'm not sure if it is going to be able to run this because the current is very high, 27 amps, which obviously it is not going to draw. I'm not bragging like without reason that it is going to draw 27 amperes from the circuit. Obviously it is not, because it is not loaded again. Okay, I keep on forgetting that first I have to test it without the boost converter and then with the boost converter. So without the boost converter, you see it's not even able to run it. Like the power supply is not good enough for it. I think I will have to give pulse speed because the starting current is going to be huge. It is always huge. Maximum current 26 amps at the start. Now we have achieved full speed because I gave it like a current in pulses, so the power supply was not that much loaded as it was initially. Initially it was like what have you connected, it is so big load, can't you see that I cannot handle that much load? But in pulses, yeah, okay, I can handle it, then I cannot, then I can, and finally it runs. Now guys, there is a risk since when I directly connected the power supply to this motor, it was not able to run the motor. So how is it going to be possible? Because since the voltage from the boost converter has increased, so obviously the current is going to reduce. So I'm not sure it is going to run. I don't think it is going to run, and no worries, because if I use a bigger power supply or like directly from a battery, then it will run, because of the high current inductor. It is capable of handling up to 40 amps. Let's try it anyways. Now guys, the final motor that I'm going to connect, biggest that I have, no bigger motor than this one, although the current rating of it is 7.5 amperes. The current rating for this one was 26 amperes. This one is 7.5 amperes, but its voltage is 180 volts DC. Removing the boost converter power supply terminals. It is going to run really slow. Yeah, it is at 12 volts right now. You see, torque is very good. It is at 12 volts. So you have seen the speed. Now let's move on to the part of boost converter. Circuit. Okay. Wow. Do you see the speed? It is so good. At present it is running somewhere between 35 to 40 volts, because obviously it is such a big motor, and the voltage is going to drop when loaded a little bit just at the beginning, but then it is going to be it is not going to drop then easily. I've disconnected the supply. Oops, this wire came out. Beware of the heat sink. Anyways, so guys, with that I'm finishing the video. I hope you understood the making part. So that's all for today's video. Thank you so much for watching it. Please hit like and don't forget to share and subscribe. I'm so glad to share this video with you. See you in the next one. Bye bye. Hi guys, you are watching channel Mr. Electron, and today in this video what I have for you is this really old motherboard with a Pentium 3 processor. It's from 2010. Okay, so let's get started with this CPU fan, because my plan is to remove its driving circuit and then do some rewinding on its armature so as to find out if we can run this motor or this fan directly on AC supply without any circuit. Please note that this video is more of an educational or research type and not a DIY type, so make your conclusions accordingly. With that being said, let's get started. So guys, now I'm going to test this fan with this power supply. At present it's set to 12.6 volts. Okay. So the good thing is that yes, it's working. Let's increase input voltage. So that's the maximum voltage, 24 volts, although this fan is just 12 volts. Still I'm running it at 24 volts. Now guys, let's measure the winding thickness. Previous winding, which was this one. And here we have 0.07 mm. And in place of that, I'm going to use this wire. It's a little thicker. Let's show you the size. 0.41 mm, almost 6 times more thicker. So guys, here I've provided 20 turns for each pole. Now guys, I have this habit of testing my projects before sharing it with you guys. So behind the scenes, the armature got damaged after working for some time. And for that reason, I took another bigger CPU fan so that I get more space for the armature slot winding. So I broke off its driver circuit, removed its initial winding, and then rewound it with the same size of wire, but this time the turns are 70 per pole. And here, as you can see, only 2 wires coming out because for the other poles I have provided the tappings. So let's try it on AC supply 12 volts. And guys, for this experiment I am not going to use the tapping points, only the end points, these 2 wires. And you see this marker slot, it's gonna go like this, and we have our fan. Now guys, this is our 220 volts to 12 volts transformer, and that's our 220 volts home socket supply. As you can see, 246 volts. And now that I've connected the transformer in between, the output voltage as measured here is around 12 volts AC. Okay, so turning on the supply, let's see if it runs or not. No, it's not starting. On close-up, we can see that there is a lot of vibration. Now, I'm going to explain it to you with the help of this diagram. Hey, did you know that your most valuable details like your bank account information, passwords for online activity, emails are all at a great risk because hackers are targeting your internet activity with an exposed IP. So don't wait. Choose the best NordVPN service now. Please note that huge discount is available. Both link and your coupon code are available in the description. So grab it now. This middle thing that you see is the armature, which is this one, 4 poles and 4 poles here. And this ring that you see, that represents magnetic ring, which is here in this fan. This ring, you see, it's sticking. So what happens is, when we give 12 volts AC supply to the end wires of the winding, because of the AC input voltage, these poles start changing. Like initially, if it was north, south, north and south, it is going to change from north to south here, similarly north here, and then south here, north here. And this process is going to continue as long as the armature is getting its power from the AC supply. Now this is electromagnet, so the polarity can change infinitely, but this piece, the magnetic ring, it's permanent magnet. Let's say that this side is north, constant north, okay, this is south, this one is also south, and this one is north. At the first cycle, when it is the top for the AC input, at the first cycle, let's say this electromagnetic pole is south as written over here, and this one becomes north, this south, and this is north. So when the electromagnetic poles are compared to the permanent magnetic poles, south is facing north of the permanent magnet, north is facing south of the permanent magnet, and so for the rest of the poles. Because of which this armature locks the permanent magnet to itself and there is no motion of the fan at all. But as soon as we go to the negative cycle, this north will remain north, south, because it is permanent magnet and the position also did not change. But this south is going to become north because of this changing sine wave. We are in the negative cycle, this cycle. So I've cut off the south. It is going to become north once again. This south, north, and this one south. So this time, if you will note that north is facing north, south, south, north, north, and south is facing south. So every pole on the permanent magnet and the electromagnet is going to repel each other, because of which this permanent magnet is going to try and start to move and relocate its position from this place. Like this is north, so this north is going to try and come to this place or this place, because here we can find south and opposite polarities attract. So north is going to either try to come over here or try to come over here, because at these points it is finding the south pole. But as soon as it tries to rotate, the polarity is going to change, because the cycle is going to move from the negative again to the positive, and this north will again go to south, and this is going to become north, this south, and this north. So then it is going to think that why move, because I have south over here. The field is changing at such a high speed because of the AC changing poles that it is going to vibrate at one point. But if the changing frequency was very small or very less, like maybe 2 changes in 1 second, then there could have been a possibility that this magnetic ring got locked with the armature poles. There would have been a possibility, but at present the frequency is 50 Hz from our home socket supply, so it just can't catch up, and hence the vibration. Now guys, let's turn it on once again, and this time I'm going to push it close to the synchronous speed. You see? And now it is working on its own, because the poles of the permanent magnet have been synchronized with the electromagnetic poles, and like even if I try to stop it now, it is synced. So now it is working like a synchronous motor. I'm trying to stop it, but still, yeah, if I push it too hard, the transformer is not powerful enough. Yeah. See, no circuit at all, and it is running. But yes, still this is just for research. It is not practical because we cannot do this all the time. Now let's turn it off. Now guys, I'm going to show you a magic. This time I'm going to connect it to a power supply, and I'm not going to push it, but still it is going to start. Okay, so starting it. So the poles are synchronized and it's running. No circuit, only winding. And I'm going to increase the speed. So now I'm going to give you a close up on that. As I said on the diagram that it can get to any direction it wants. Let's try and make it to clock. Yeah, and we have clockwise direction. So guys, let me know in the comment section how I started it without pushing it.